Hi, I'm Hanis, and we are Team 1 from Lab Group P8. Our abstract engine is built around a central class called GameMaster. Main is the entry point, it does zero game logic. It just creates GameMaster and forwards lifecycle callbacks. GameMaster is a singleton and acts as a mediator, where it owns all 5 managers and they communicate through it, and never directly with each other. For demo purposes, at startup, main registers 3 scenes, menu, game, and settings, then loads the menu. After that, every frame runs through a fixed 5-step loop. 1. IO Manager processes input. 2. Entity Manager updates entities and removes any flagged from removal. 3. Movement Manager moves entities, skipped when an overlay is active. 4. Collision Manager detects collisions and flags them, and removal happens next frame in step 2. 5. Scene Manager updates the current scene and overlays, and after that, Game Master renders through Output Manager and Display Manager. Now, I'll hand over my time to Saying.
To start off, we have the core section of our UML diagram, which has 2 classes, main and GameMaster. Main is dependent on GameMaster, and this section is in charge of initializing our abstract engine. Moving on to collision management, we have a collision manager, iCollidable, and collidable entity. The purpose of this management is to detect collisions and determine the course of action upon successful detection. For entity management, we have entity manager, abstract entity, iMovable, and base entity. The entity management is responsible for creating, removing, updating, rendering, and disposing of entities. Next, for movement management, we have movement manager, move playable entity, and move non-playable entity. These are responsible for movement of the playable and non-playable entities. Moving on to scene management, we have scene manager, base screen, menu screen, game screen, and settings screen that are here too. This management is responsible for initializing the scenes and transitioning between scenes as well as to implement all the other managements. Lastly, for I/O management, we have a I/O manager and split into 2 sub-managers, input and output manager, as well as a number of interfaces and classes to manage input and output. They are responsible for user input and output such as keyboard, audio, display, and mouse. This sums up the overview of our UML diagram, which will be shown in greater detail in the following sections of this presentation.
Thank you, Sheen. Now I'll be talking about the collision management. The purpose of this subsystem is to handle interaction between entities in the simulator world, specifically the ramdraw and the bucket. Collision detection is implemented using as is online bounding box or AABB, where we check for rectangle overlaps using getBounds.overlaps. When an overlap is detected, the collision managers trigger the onCollision method. Importantly, the managers only perform detections and does not contain any gameplay rules. Collisions response is handled by the entities themselves through polymorphism. The iCollidable interface defines the collisions contract, while collidable entities store shared collision state, such as the collider flag. This ensures encapsulations and clear separations of responsibility, aligning with the single responsibility principle. In terms of scalability, the current implementation uses OR-N² pairwise detections, which is sufficient for small simulations. A future improvement would be spatial partitioning techniques to reduce unnecessary collision checks. This design achieves modularity, reusability, and clean object-oriented structures. Now I will hand over to Hanis.
Thank you, JY. Scene Manager is a singleton that handles scene registration, transitions, and overlays. Scenes are stored in a hash map by name, and when we call a load scene, it follows a lifecycle, which pauses the old scene, activates the new one, and then calls initialize. We also built an overlay system using show overlay, which pushes a screen on top of the current scene. The main scene remains visible underneath, but its logic is paused. In terms of OOP principles, for inheritance, all screens extend base screen. For abstraction, initialize is an abstract method, so each screen defines its own setup. For polymorphism, Scene Manager holds a base screen reference. By runtime, the correct subclass method is called. And for encapsulation, all internal state is private and only accessible through the public API. For OCP, adding a new screen is as simple as extending base screen and registering it, and Scene Manager does not need to change. And for SRP, Scene Manager only manages scene state and lifecycle. Rendering is handled separately by Display Manager. Now, I'll hand over my time to Ikwan.
Thanks, Hanis. Hi, I'm Ikwan, and I'll explain about the I/O management. The I/O management has a lot of subparts as it's used extensively throughout many of the other systems. I/O manager handles all input and output by delegating to input and output managers. They have a has-a relationship exhibiting composition. For input, when a key is pressed, libjdx input is the concrete class that wraps the actual libjdx calls, isolating the framework to one place. It sits behind the input source interface, so the controller manager never touches libjdx directly, thus showing abstraction. Controller manager then maps a key code to an action using its bindings maps, which is private and only exposed as a read-only copy, thus showing encapsulation. The game logic checks actions and not the physical keys. At startup, KeyBindLoader loads binding from a JSON file, so controls can be changed without modifying code. Mouse Manager handles mouse state, though it's unused in practice, but it shows the system is extensible. For output, Output Manager delegates to 3 components, mainly Display Manager, which handles render order through iRenderPort, Audio Manager handling sound through iAudioPort, and Log Manager handles debugging logging to console through iLogPort. Each of them with their own single responsibility, thus follow single responsibility principle. And because they're behind interfaces, implementations can be swapped without changing output manager, thus showing polymorphism. Every frame, Game Master calls IOManager.update to poll input and then passes the current scene and overlays to Output Manager for rendering. When the raindrop is collected, Output Manager plays the drip sounds and logs it. For the input, here's a feature for easy rebinding. Rather than manually hardcoding, the action enum defines what the player can do. Keybindings.json found in assets would map each action to a physical key. Keybinder loader reads these at startup and feeds it to controller manager, overwriting any default controls set in the binding tab. New bindings and new input sources can be added without modifying existing classes or the code, thus showing OCP principle. Now I'll pass the time to Xiying.
Thank you, Ikwan. Now I'll be talking more about the movement management. Starting with the movement manager file, it handles movement and their logic for playable and non-playable entities. Based on the Boolean result retrieved from getPlayStatus through iMovable, if the Boolean result is true, it routes the entity to playable entity. Else, it gets routed to non-playable entity. Moving on to move playable entity, based on the keys pressed that the IO management detects, it determines the direction that the playable entity moves. This class also updates movement for the playable entities based on the direction that the entity moves in. For move non-playable entity, it determines the movement of the non-playable entities. In this case, we set the non-playable entities to fall at a constant speed. Lastly, for iMovable, it allows entities to apply movement methods as well as to get the Boolean value of getPlayStatus method to be used in Movement Manager. The OOP principles applied to movement management are inheritance and interfaces. Inheritance is implemented with the three classes Movement Manager, Move Playable Entity, and Move Non-Playable Entity. The Movement Manager as the parent class routes the entities to the subclasses based on the getPlayStatus Boolean value. Interfaces is implemented through iMovable, and it allows the entities to have movement methods as well as to get the return value from getPlayStatus, which is determined when the entities are created. This concludes the overview of the movement management. I'll be passing the time over to Yisheng. Thank you.
Thank you, Singh. Now I will be giving an overview of our entity management. We begin at the foundation with abstractEntity.java. This class uses abstraction to define what every object is, a unique ID and a set of x and y coordinates. It also forces every subclass to implement its own update logic. It also uses encapsulation by making the coordinates and IDs private and only accessible via the setter and getter methods. Here we can see the setter and getter methods, and here we can see the ID is private. These objects are controlled by the EntityManager.java. Entity Manager stores all entities inheriting abstract entity in a centralized list and handles the game loop. It also clears all entities using the dispose function, shown here, and the Entity Manager also uses encapsulation by making the list private and providing a getter function, shown here and here. The update method in Entity Manager is a case of polymorphism, as when it runs, it can run two different types of logic for the objects depending on whether they are playable or non-playable. Now for iMovable and iCollidable, they give the entities behaviors based on whether they are playable or not. It ensures that the object can calculate its own frame adjusted speed, and iCollidable bridges our entities to the collision system, adding a Boolean state to track hits. Everything converges in the base entity.java where we merge movement data, collision logic, and textures into one template, as shown here, as well as here. We then use inheritance to create specific roles such as playable entities and non-playable entities for objects such as the bucket and raindrop. Finally, the entity spawner.java is responsible for calculating the random start positions and injecting the new instances directly into Entity Manager. That's all for our presentation. Thank you for your time.
Hi, I'm Christina and I'll be demonstrating our abstract engine and briefly explain how its components work. So for the scene part, every scene follows the same structure. It can be rendered, disposed, and resized properly. For example, pressing the enter in the menu loads the game screen and pressing back the backspace button for the menu screen, all without changing the engine's core logic. We also have an overlay system for things like pause menu, which can display screens on top of the current scene while stopping the simulation, such as the settings screen. Additionally, each scene can handle window resizing so the content adapts dynamically if the user wants to change the window size. Next is entity. Entities like the bucket and raindrops share basic properties like position and ID. Playable entities like the bucket are controlled by the player, while non-playable entities like raindrop move automatically. The entity manager keeps track of all entities, updates them, and removes them when necessary, for instance, when a raindrop is caught or fall off the screen. Now let's move on to movement. Movement is handled by Movement Manager, where it checks all entity and decides how each one should move. If the entity is playable, like the bucket, its movement depends on player input like pressing the arrow keys to move left, right, up, or down. If the entity is non-playable, like the raindrops, it follows the AI movement logic where it is not controlled by the user inputs. In our case, the droplet simply falls down from the screen. For collision, the collision manager checks if entity boundaries overlap. For example, when the raindrop collides with the bucket, the engine detects overlap and calls on collision method for both objects. It is then marked as collided. Once marked, the entity manager will remove it from the entity list in the next cycle. Lastly, we have I/O. On the input side, input manager maps the action like move left or pause to keys. For example, P is for settings, whereas Q is for close, and backspace for menu, and then press enter to start simulation again. Our key bindings aren't hard-coded, they are loaded under keybinds.json so that actions can be rebinded for other keys. So when the game starts, the keybind loader loads keybinds from keybind.json, and if the file is missing, the system logs an error and falls back to the default keys. So on the output side, the output manager handles rendering through display manager, playing sounds with audio manager. For example, when a raindrop is hot, a sound effect is played to demonstrate that the audio system is working.